Welcome to AP Podcast 13.3. This is on equilibrium and pressure, and we're just continuing our journey with equilibrium. But instead of dealing with a situation where we have concentrations and molarity, we're going to deal with gases. And then, of course, when you have gases, you have pressures, right? So this all has to do with gases and pressures, and we could treat them exactly like we did with the concentrations. So if I was going to write the equilibrium expression for something like this, here's a reaction. We're getting some sulfur dioxide plus some O2, making sulfur trioxide. I would write it just like I did before, K equals, and then instead of using a bracket that indicates a concentration, I would just go SO2 cubed, again products over reactants, over SO2 squared times, oh, I'm sorry, I did a cube. You guys are probably yelling at the screen. That's a 2 over O2. All right. So notice we're calculating exactly the same way. But the parentheses, is what we're going to use for gases, and the brackets is for concentration. So that's kind of what I've drawn out here. If you look at the second one, we've got gases. If it were a situation where instead of seeing the G like we see, instead of up here we would see AQ, right? If we saw AQ everywhere, then we would be looking at this one right here. But the nice thing is even though we're writing it just a little differently, the calculating part is exactly the same. Alright, so here's a little problem, and go ahead and pause the video and see what you get. Do it just like we did with concentrations. Alright, if you worked it out correctly, you would get a value that K equals 5.2 times 10 to the fourth, which is pretty big, right? So there you have it. And again, if this is something that you didn't get, try it again. And if not, we'll definitely go over it in class tomorrow. But it should work out okay if you did it right. All right, so let's try another problem. And this is just more of an exercise in math. They've given us the equilibrium constant, and they want us to find the concentration of NO2. So I'm going to write this out, but if you would, just pause the video and try and do it on your own and see if you can get it. Alright, did you get a value of 0.600? Okay, did you get that? Well, if not, let's just see how we do it. If I were to write out the equilibrium expression, I'd go K equals NO2 squared over N2O4, right? Now, I know what K is, so I'll put that in there, 0.133, right? And what else do I know? I know at equilibrium that the pressure was 0.271 for N2O4. So I still don't know this up here, NO2 squared, and then I know that this is 2.71, right? So again, if I just take this number over here and multiply it by that one, I get 0.360, and that equals NO2 squared, right? So I still have to get rid of the square, so what should I do? And since you guys are all mathematical geniuses, go, well, I got to square root both sides, right? So when I take the square root of that number, I get that one right there, right? So hopefully that wasn't too bad. All right, now let's look at another thing, because sometimes you'll be given a problem in AP where they want you to equate the concentration of K to the pressure of K. In other words, Kc versus Kp. So let's look at that one. Alright, so you can see from right here we have this new equation, and the good news is this equation is on your equation sheet. You can see that the equilibrium with the pressure is related to K, and this you can think of this as Kc, that's for the concentration when we have molarity, equals K times RT raised to a power of N. And all N is the sum of these products coefficients minus the reactant coefficients. And so it makes it relatively simple. Now, why in the world are they related to each other by an RT? I just want to show you a simple reason why. If we think of Pivnert, okay, if I were to put P over here and put V under there, right? P equals nRT over V. Well, what we get right here is N over V. which is moles over liters, right? And what that is that's the concentration of the gas, all right? And the concentration of the gas is similar to the concentration of a liquid when we're talking about aqueous solutions. And so what oh my goodness, I can't remember the word. What variables are still there? It's the gas constant times the temperature. So those still play a role. Now, if you want to look at a nice little derivation on how they relate that to Pivnert, our book does it really well in this section. And that stuff is just kind of beyond what we need to know. But if you're really curious about it, you can definitely find it. So let's try a problem or two on this stuff and see how we do. So there you have it. We've got this reaction. They give us the K, and they want us to figure out what the K is at this temperature. And I guess I should say the Kp, right? Okay, so what I'm going to do is I'm just going to start plugging in the numbers. And Kp equals the K, which in this case is 2.01 times 10 to the fourth, right? Times my RT factor, right? Well, what's R? Let's see. It's 25. Oh, pardon me. It's 0.0821, right? And then my T is 25 plus 273, so times 298. Okay. And I guess I'm going to put that all in brackets. And then we've got to raise it to a power up here, right? And remember, it's the coefficients of the products minus reactants. Well, what do I have here? I have 1 minus, right, because there's a 1 right here, minus 2, right? So it's 1 minus 2, which equals negative 1. Okay, so that's to the negative 1, which is the reciprocal, right? So when you work that out, and again, work with your calculator, hopefully you get this, I get 821, all right? So there's a problem. Let's try one more, make sure we're all on the right page. All right, if you want, pause the video, give it a shot. I'll show you my answer in just a second, and let's see how you did. All right, so I got 0.335, and hopefully you did too. Notice up here that my exponent was 1, which is just the number, right? So, and that was because I've got 3 minus 2, so I got 1, and so that worked out. So hopefully you got that. Let's do one more little practice, and then we'll be done. All right. For which reaction in 31 does Kp equal K? So now I haven't gone over when this would be the case, but look at it for a second and let's just see what it would be. Pause the video and try it. Okay, little brain fart here. Unfortunately, I have not given you enough information, so if you had no idea what I was talking about, don't feel bad. This is my problem. We haven't got to the part where we talk about how solids are not a part of the equilibrium expression. That's coming, so I apologize for that. But I need to get this point across right here, because this is an important thing, right? Now, if we go back to the equation that relates these two, I just want you to look at this, because this is an important thing, because sometimes this question will pop up. How does Kp relate to Kp or Kc? Or, what are they equal? Well, imagine what would happen if I had a reaction where the coefficients of the reactants equaled the coefficients of the products. Like in this situation, I would get 2 minus 2 equals 0, right? Well, in this case, if I raise something to a 0 power, what does the value of RT become? Well, as you guys know, it becomes 1, right? So 1 times K equals Kp. So if you ever have a situation where the coefficients are the same, Kp and K little c are equivalent. And so sorry about throwing in that practice question there, but hopefully that'll make sense. So again, we'll go over any of this tomorrow if you need to, and see you next time.